Hello everyone again. Now I would like to share some research that I have done for the last couple of years with you. The first one uh, actually is does include a couple of parts of my PhD dissertation. Uh, it is called the on uh, statistically Köthe-Toeplitz duels. So when I was doing my PhD research, I focused on uh, finding some uh, alpha, beta, and gamma duals of some spaces that I was studying with. Uh, the main target was uh, to generalize the concept of statistical boundedness to generalized different sequences. So even though we did not include the concept of statistical boundedness in our previous talks, it is worth noting what a statistically bounded sequence is. As you can see here, a real number sequence X is statistically bounded if there exists a positive number cap B such that the density of this set is 0. This definition was given by Friede. So I tried to generalize this idea for this generalized different sequences. So this was the second part of this paper, which dealt with the concept of delta M statistical boundedness of sequences. So we say that X is called delta M statistically bounded if there exists a non-negative real number L such that these conditions hold. So as we discussed before, whenever we come up with a new concept of convergence or boundedness, we would love to have some particular examples that do not meet the main definition. For example, if we take a sequence as this, we see that this sequence is not delta statistically bounded with order 1. And we give some basic results about the relationship between statistical convergence and statistical boundedness for generalized difference sequences. So in this proposition, we talk about the relationship between boundedness and statistically boundedness for generalized difference sequences. We say that every delta m bounded sequence is delta m statistically bounded, but the converse does not have to be true in general. We gave a couple of we gave an example of sequence that showed that the converse is not does not have to be true for some particular cases. In this proposition, we discussed every delta m statistically Cauchy sequence is delta m statistically bounded, but the converse is not true. So we wanted to give useful characterization for a sequence to be delta m statistically bounded. Since we needed a lemma to prove our claim in the coming theorem, we needed such an lemma. If E is a subset of natural numbers with infinite cardinality, and uh, it also has a complement in N with infinite cardinality, then there exists an increasing sequence of natural numbers mj and nj such that E equals to infinite union of these intersections, where nj is between mj and mj plus 1 for all j's. So after doing it, we say that a sequence X is delta M statistically bounded if and only if there is a delta M bounded sequence Y such that delta M xk equals delta M yk for almost all k. As you may remember, the concepts that we talked in the morning, one of them was the concept of almost all k. We need to underline that this means that we have this equality for a subset of natural numbers having density 1. So this equality happens on an index that has a density 1 with natural sense. So after this, we try to find some Köthe-Toeplitz duals of space of all delta m statistically bounded sequences. In this theorem, we see that the alpha, beta, gamma, delta, or n duals of all statistically null sequences are all equal to phi, which is finitely many non-zero terms of spaces, the sequence space. Thanks to this theorem 3.1, we have a corollary saying that all statistically convergent sequences and the space of all statistically bounded sequences has the same dual with alpha, beta, gamma, delta, and n sense as the same with statistically null sequences, which is phi, the space of all sequences with finitely many non-zero terms. So this idea made us think about a more generalized version of the concept of duality. Before that, we used a couple of proposition and theorem to show that the alpha, beta, gamma, delta, n, and cap n dual of the space of all delta m statistically bounded sequences has all phi as the duals. So we wanted to extend the concept of duality to statistical sense. So to do this, we needed to come up with an idea which generalized the idea of summability of infinite series to the statistical summability of infinite series. So to do this, we define what statistically summable series is. In the literature, we see that Tripathi gave an initial definition of statistically summable series, which is basically based on the statistical convergence of the sequence of partial sums. But in our definition, we took a little bit a different way. We say that this is the, I believe this is the most crucial definition of this work. We say that the sequence X is said to be statistically summable to L if there exists dense subset of N, which means the density of A equals 1, and xk is xk is summable over xk is xk is a convergent series on the set of cap A. So by this definition, we arrived at the initial generalization of the concepts of duality with respect to statistical sense. The statistical alpha dual of X is given by this way. It is a subset of sequences such that the product of xk and yk forms statistically summable convergent series with absolute values, sorry, and we say that the statistical beta dual of x consists of sequences such that for each y from x, the product of xk and yk is statistically summable within this sense. So in the first couple of proposition we discuss some properties equivalent to the ordinary case of duality. So in this theorem we compute the statistical duals of some well-known spaces which include C naught, C, L infinity, S C naught, S C B, S B, respectively, the space of all null sequences, the space of all convergence sequences, the space of all bounded sequences, the space of all statistically convergent sequences with zero limit, space of all statistical convergence sequences, and space of all statistically bounded sequences. We prove that all these subspaces, all these sequence spaces has statistically alpha and statistically beta dual as LB, which is defined here. This is an extension of the space of all absolutely convergent summable series. As you can see, we say that X is in LB if X is absolutely summable over a subset of E with density 1. So here we give some equivalent of notions about sequence spaces. For example, one of them is statistical normality of a sequence space. We say that let UK be in UK be any sequence and X be a sequence space if the absolute value of UK less than or equal to absolute value of xk for all k in cap E such that E has density 1 for some sequence from X implies U being in X, then we say that X is statistically normal or statistically solid space. X is statistically normal if we have this inclusion for short. I mean the set of the sequences U in which for which there exists some xk's from X such that we have a dense set, so that for all k from that set of cap A, uk is less than or equal to xk should be included by cap X. So we defined a couple of notions which are equivalent of from usual case: statistical alpha space, statistical beta space, or in other words, statistically perfect space or statistically quoted space. In this theorem, we prove that LB that we defined before is a statistically perfect space. In this theorem, we show that every statistically perfect space is statistically normal. And as an immediate corollary, we express that LB is statistically normal. So, as a second research that I would like to share with you, we try to generalize the idea of statistical boundedness of sequences with deferred sense and modulated sense. This paper is titled as "On Deferred F Statistical Boundedness." We give some historical information about the literature here, and some information about modulus functions. This is a very crucial property of modulus functions obtained by Maddox. For any modulus f, the limit of f of t over t exists. Sorry. So if a subset of A has this property, which says that the limit of this ratio exists, then we say that this unique number is the deferred F density of subset A. This concept was given by Gupta and Bhardwaj, and as Aispurus and others' first paper from 2014 remarked, this equality does not hold for some particular modulus functions. So we say that a sequence xk is said to be deferred F statistically convergent to L, provided that this subset, this set of natural numbers, is a null is a null uh, subset with respect to this new density. So we give some basic results about this type of density. And here we give the main definition of the paper. What is deferred statistical bounded sequence? We say that we say that the sequence X is deferred statistically bounded if there exists some positive number m such that this limit is 0. In other words, this subset has density 0 with this sense. With some selecting of particular cases of modulus function or deferred sequences, we see that the concept of deferred statistical boundedness extends the concepts of deferred statistical boundedness, statistical boundedness, and statistical boundedness. Here we give equivalent result to that of Aispur and others gave in 2014. We say that every deferred statistically bounded sequence is deferred statistically bounded with the same technique. But this example shows that the converse of this result does not have to be true for some special cases of modulus functions and deferred functions. If we take f as log t plus 1 and qn as n to the power 2 and pn as this definition, and x be defined by that way, xk equals to n if k equals n square for some n, and xk is 1 if k is an even non-square, and xk is 0 if k is an odd non-square. And with some computations, we see that x is deferred statistically bounded, but on the other hand, by the help of the function log t plus 1, we prove that we show that x is not f deferred statistically bounded. Yeah, in this theorem we show that the space of all f deferred statistically convergent sequences is included by the space of all f deferred statistically bounded sequences properly. here we give an example showing that there exists some sequences which are deferred F is statistically bounded, but not deferred F is statistically convergent. Here we say that L infinity, the space of all bounded sequences, is included by the space of all deferred F is statistically bounded sequences. And in this theorem 2.4, we establish a structure theorem for deferred F statistical bounded sequences. We say that X is in SBFPQ if and only if there exists a null set of A with this density type such that xk is a bounded sequence on the complement of this set of A. This is a useful characterization for a sequence xk to be deferred F is statistically bounded. As the sequence xk is deferred F is statistically bounded if and only if there exists a sequence y from bounded sequences such that xk equals to yk for almost all k deferred with respect to modulus function f. So in this result we present a decomposition theorem for deferred F statistical boundedness. We say that SBPQF is sum of L infinity and the space of all F deferred null sequences with respect to modulus function F, but not uniquely, because the intersection of these two space have some sequences which are not zero sequence. In this theorem, we give a Tauberian result about the concept of deferred F statistically convergence and concept of deferred F statistically boundedness. As we mentioned before, every F statistically convergent F deferred statistically convergent sequence is F deferred statistically bounded, but not conversely. But if xk is a monotone sequence and it is deferred F statistically bounded, then it is deferred F statistically convergent. This is a generalization of a very well-known property of bounded sequences with monotone sequences which are bounded. So thanks to this theorem, we can say that deferred F statistical convergence and deferred F statistical boundedness coincide for monotone sequences. And these parts we deal with the competition of alpha and beta duals of the space of all deferred F statistically convergent sequences and the space of all F deferred statistically bounded sequences. In this second part, we deal with some conditions to see the relationship between statistical boundedness with modulus sense and statistical boundedness with modulus sense and deferred sense. If if this sequence is a bounded sequence, then F statistical boundedness implies deferred F statistically boundedness. In this theorem, we discuss an inclusion theorem, an inclusion between deferred F statistical bounded spaces with different pairs of deferred sequences. And this is another theorem showing the relationship between between deferred F statistical boundedness with different pairs of deferred sequences. In this part, we discuss the concept of deferred F statistical boundedness under different type of modulus functions. We say that if we have two modulus functions satisfying this property, then in this case a sequence which is deferred G statistical bounded, then it is deferred F statistically bounded. In this theorem, we show that two types of deferred F statistical boundedness with different modulus functions are equivalent if this limit exists finitely as a positive number. We say that if the limit of f of t over g of t exists positively and finitely, then xk being in SP G PQ if and only if xk is in SP F PQ. Yeah. So after we dealt with some generalizations of statistical convergence and statistical boundedness within for the sequence of real numbers, we wanted to challenge ourselves for the different type of sequences that are not necessarily from real numbers. One of them was given for nets, not just sequences. As you know, the concept of net, a net generalize the concept of natural number. Generalize the concept of a sequence. So since the concept of a net is related to the concept of measure, we give a definition from another paper that we published earlier, statistical convergence of nets in real spaces. Which says that let A be a directed set. I'm sorry, maybe I should have reminded you what a directed set. Sorry. Okay, maybe first we need to remember what a real space is. A real space is an ordered vector space with a partial order relation having some properties. Yeah, we say that a binary relation, on a set A is called preorder if it is reflexive and transitive. A non-empty set A with a preorder binary relation is said to be directed upwards or shortly directed set if for each x a from A there exists a z such that x is less than or equal to z and y is less than or equal to z. So here I just need to emphasize that this is not necessarily the usual inequality of numbers. This is a much more generalized version of it. Unless otherwise, sorry. For a given elements of A and B in a preordered set A such that A is less than or equal to B, the set X, the set of X's from A that is between A and B with this preorder relation is called an order interval in A. A subset I of A is called an order bounded set whenever I is contained in some order intervals. So let A be a directed set and cap M be a subfield of P of A, which is the power set of cap A. An order interval AB of A is said to be finite order interval if it is a finite subset. A couple of condition is given here. So following from the previous paper that we talked, the directed set measure is an extension of the natural density that we dealt with before. So by this definition, we make sure that directed set measure, the directed set measure is an extension of the natural density. So we say that a real vector space E with an order relation is called an order vector space if for each x and I from E with x is less than or equal to y, the inequalities, the two inequality holds for all z from E and alpha from positive real numbers. An ordered vector space E is called a Rees space or a vector lattice if for any two vectors x and I, the infimum and the supremum of x and I exists in E respectively. So this is the original part of the paper here, statistically topological convergence. Yes, so we take net in a locally solid Risk space. Here A is a directed set within the sense that we mentioned in the beginning, and we take alphas from this directed set. So let x alpha be a net in a locally solid Risk space. Then this net is called mu statistically topological convergent to x in E if for every 0 tau neighborhood of U there exists an index alpha U related to U cap U such that the measure of this set is equals 0. If we take A as the set of all natural numbers, then we see that this concept reduces to the statistical convergence in topological spaces. So this definition is a generalized version of the original concept for locally solid Rees spaces. So we give some crucial definitions here. One of them is called straight mu statistical topological convergence for in locally solid Rees spaces. And this is an example about this concept. And in the third part, we deal with results on mu statistically topological convergence on locally solid Rees spaces. So I don't want to take much of your time. I'm gonna be a little bit faster. So this is the most current paper that I published, which is entitled by Statistical Convergence and statistical continuity through deferred Cesaro mean in locally solid Riesz spaces. We give some historical information about the concept of deferred density here, and some preliminary results on the locally solid Riesz spaces. So we say that a sequence of a sequence in R locally solid Riesz space is named to be deferred statistically tau convergent to a point sigma in R if the set of mu has zero deferred density for each u neighborhood of 0, where mu is defined by this. In the following examples, we see that there are some sequences in some locally solid Riesz spaces that are convergent with this sense, and there are some others that are not convergent with the new sense. For example, to do this, we use the locally solid Riesz space of all null sequences. So we can observe that the solid base of zero consists of the open neighborhoods which are given by that way. So if we define a sequence of sequences in C naught by this definition, xm is defined by that way, and take any neighborhood from zeros, class of neighborhood of zeros, then we see that we have this equality implying t is finite, implying t has zero density since t is finite. Then because of this, we say that the limit of xm with this sense is equal to zero vector in locally solid Riesz space C naught. So in this example, we show that there exist some sequences which are not deferred statistically tau convergent to any sequence in C naught. For example, the sequence of all unit vectors, in C naught cannot converge to any zero sequence with this sense. Here we give a more generalized equivalent of cochiness of a sequence in a locally solid real space. We say that a sequence in R locally solid real space is called deferred statistically tau Cauchy if there is a number T from natural numbers such that the density of inserted set is 0. I'm sorry. For every uh, neighborhood of 0. Um, in this theorem, we prove some basic and useful properties of deferred statistically tau convergent sequences in an locally solid real space. We see that uh, if a sequence if a sequence is uh, is deferred statistically tau convergent to a vector, then this limit has to be unique if the topology endowed in R is a Hausdorff topology. And we see that if we have two deferred statistically tau convergent sequence and if we uh, sum them or if we subtract them with then we see that the summation of these sequences also deferred statistically tau convergent to the summation of their limits. So here we show that if we have three sequences from a locally solid real space such that we have a such inequality with this order for all m, then we say that if limit of xm and limit of zm is the same with this sense, then the limit of ym has to be the same limit given given in the beginning, sorry. So here we show that every deferred statistically tau convergent sequence is deferred statistically tau Cauchy in an locally solid real space. In the following theorem, a sufficient condition is presented for a sequence in an locally solid real space to be deferred statistically tau convergent. We say that if the limit of xm with this sense equals to sigma, sorry, if there exists an index set of natural numbers which is deferred dense, so that the limit of xme equals sigma, then we say that this sequence is convergent to the same limit with this sense. So here we give some inclusion theorems between different type of uh, uh, deferred to statistically convergent sequences of sequences in a certain locally solid risk space. If we have two deferred pairs, and if we see that this holds, then we say that uh, as tau limit of xm, if as tau limit of xm equals sigma, then as tau ab limit of xm is sigma. So we give some additional results with different pairs of deferred sequences. And we continue doing that with under some different conditions. And in the last part, we extend the idea of continuity to deferred statistical continuity in locally solid risk spaces. And in this theorem 9, uniform continuity, we prove that uniform continuity implies deferred statistical continuity between LSR spaces, I mean locally solid risk spaces. And in this theorem, we show that lattice mappings are all deferred statistically continuous for any AB pair from omega, which is the set of all deferred statistical pairs holding the initial conditions that we talked about, that we talked before. And lastly, I just want to share with you an result, a couple of problems that I have been thinking on it for the last couple of years. They are related to the concept of statistical convergence series and their statistical duals. In this paper that I talked about first, we initially called a real series xk is statistically convergent to a real number L if this equality holds. However, we realized that if we revise this definition by the following, it would be much more convenient to study on. As you can see here, we say that xk is summable to L on a subset of natural numbers having density 1. But here we revise it with that way. Xk is said to be statistically summable to L provided this product is convergent to L with usual sense. Why did such a redefinition arise? One may ask. After the concept of statistically alpha and beta duality had been discussed, we formally wish to introduce statistical gamma duality, which is a little bit uh, confusing. So we wanted to change the main definition because of this set. We didn't like the way it looks, so we did not find it practical enough to research on it. So therefore we come up with the following revision at the suggestion of Jeff Conner of Ohio University. We say that the statistical gamma dual of X consists of sequences in which there exists a dense subset of natural numbers such that the supremum of this sequence is finite for every x from x. So after all, this made us have to rearrange the definition of statistical convergence of series and statistical alpha and beta duality. We can show that the two definition is pretty different by showing by having a specific example. We see that if A is subset of natural numbers having all non-square numbers, then within first series we see that the summation of xk's over cap A gives us this infinite series, while the second definition gives us a pretty different series, because the partial sums of this series are different because of their pattern. So by the revision of the original definition, we come up with a couple of new subsets of sequences, which will be called the statistical absolutely convergent series, the statistical convergent series, and statistical bounded series. We give a couple of propositions here. Then we give the advanced revised version of statistical alpha, beta, and gamma duality of sequence spaces. These are some results of this new type of statistical duality with the accordance of their usual sense. Here we redefine the concept of statistical normality under this concept. And here we have an observation that might be considered as an open question. If X is a sequence space and Xn is its uh, is a subset within the usual, a subset of all sequences within the usual sense, which saying that it has u vectors, u sequences such that there exists some sequences satisfying uk is less than or equal to xk for all k's, and x sn by sn, sorry, by Sn. Here we point out the statistical sense of the definition. It has it consists of consists of sequences from all sequences such that we have uh, we have a sequence from X, and we have a dense subset of natural numbers satisfying uk is less than or equal to xk. So because of the natural of these definitions, it is obvious that xn, the subset of xn, is included by xsn. And we, as we can remember, that x is called statistically normal provided the subset of xsn is included by x. Therefore, if x is statistically normal, then it is normal. But we show that the converse is not true in general. To me, what makes this part is different is the way of the result. I mean, generally, if we have a concept with usual sense, we say that it also satisfies the sense with statistical point of view. For example, if X is an convergent sequence, then it is statistically convergent. Or if it is bounded, then it is statistically bounded. But here we observe that if a sequence space is statistically normal, then it is normal. And we show that the converse is not true in general. And here we try to give an statistical equivalent of characterization theorem for normality, which is x is normal if and only if L infinity times x is included by x. Here AB is defined by that way. If cap A and cap B is the set of two is the set of sequences, then the product of these two space is included is consists of product of their members. Okay. Uh, yes, I see. Okay. So I'm gonna stop here. Thank you so much for listening me. Uh, okay, I guess it stopped. Sorry. Ah, here. Okay.